All right. Hopefully you all are having a fantastic evening. I just wanted to take some time to take a look at the Unit 1 study guide, go over some of the answers. My goal is to kind of not necessarily look at every single question, but at the very least every single question type. Um, and kind of like an effort to flesh out our understanding as we are moving into the test that we all have tomorrow. And we're just going to start at the beginning. Take a look at number 1, where we are asked to classify or identify what kind of number we have when we are looking at something like -1/2. Now, my advice with our classifications, this is going to be fairly universal, is to always start from the broadest definition of a number and slowly work our way in by seeing, do we meet the criteria for the next definition? And if so, then great, we can move on. If not, we can go ahead and stop. And the broadest definition that we have for any of our numbers, we'll go ahead and just list out our classifications here, kind of in order of generality. We've got the complex numbers, the real numbers, the rational numbers, the integers, and the natural numbers. Okay, I know that there are other classifications, but these are the ones that are going to be relevant for us. And we just go through the list here, starting with complex. Is a number complex? Our answer is always, always, always yes. So if you are trying to classify a number, you need to be listing C as part of your answer. In order to determine if a number meets the qualifications for a real number, we ask the question, do we see I? In this case, you'll notice that we do not have I, which would indicate that our number is imaginary, or not necessarily imaginary, I suppose, but that it would only be complex. In this particular case, notice that we do not have an I. Therefore, we can safely say that we have a real number as well. To determine if we are looking at a rational number, this is the one where it's like, does this work like a normal fraction? Are we dealing with those kind of nice, clean, solid fraction numbers? Or do we have some weirdness going on? Do we have square roots of numbers that don't simplify? Do we have, let's say, like pi or e, or really just anything that isn't going to be able to be represented nice and cleanly as a fraction? So the main ones, do we see pi? Do we see e? Do we see roots? And in this case, we say no, I don't see any of that weird stuff going on. Therefore, this would be a part of Q. For integers, we ask the question, do we have any positive or negative whole numbers? Whole numbers, in this case, the descriptor, not the classification. I know that whole numbers are also a classification, and those are just positive numbers. In this case, using it to mean not a fraction where we have like a significant denominator, where we have a non-1 denominator. In this case, you'll notice that we do not have a whole number. 1/2 does not fit the criteria for an integer. And so we would stop here. We do not meet the qualifications for Z. The only 3 classifications that we could consider and that we need to consider are C, R, and Q. But while we're here, might as well mention it. If we did, in fact, pass the test for Z, we could move on to N. And N is just looking at those positive whole numbers. I guess I should also mention, while we're here, 0 would also technically count in the integers. 0 is technically not positive and also not negative. So it wouldn't count as a natural number where we only take positive numbers, but it would count as an integer. All right. Let's take a look at number 6 next. Jumping ahead a little bit, a lot of like some class. But actually, before we jump to number 6, let's take a look at number 3. So number 3, true or false? Ask the question: if a number is real, is it also complex? Now we can generate numbers that are real. And the question is, can we find one that does not meet the definition of C? This one, hopefully, kind of fairly self-evident. Since all of our numbers are complex, all real numbers must also be complex. So it is a true statement to say that all real numbers are also complex. That is absolutely true. We are comparing it to like a broader definition. So there aren't any real numbers that don't fit that criteria. Fantastic. Okay. Number 6. In this case, we are given a function. Not the kind of typical way that we see a function, but just kind of a set of inputs and outputs here. So our first kind of coordinate pair here, 1, 2, and then 3, 4, and then 5, 6, and then 7, 8. And we are being asked to introduce a new mapping into this particular function in order to make it not a function. So what does it mean for a mapping to be a function or not? Well, this comes down to that idea of, is what we are looking at well-defined or is it not well-defined? And a well-defined map we can have by looking at, do we have any repeated values of x? So for function, we ask the question, do we have repeated values of x? You'll notice in this case that there are no values of x that are repeated, right? We use 1 exactly once, we use 3 exactly once, we use 5 exactly once, we use 7 exactly once. We just need to use one of those values again. And so introducing a point, let's say 3, -7, creates an issue where if I ask the question, what is f of 3, it's either going to be 4 or it's going to be -7. And because we have that ambiguity, this would not be well defined. And therefore not a function. So any point where the x value matches one of the x values that we've already used, and importantly, takes us to a new y value for that particular x value. For instance, if I tried to introduce the point, let's say like 3, 4, which you'll notice is already in my list. Technically speaking, we do have a repeated value of x here, but it doesn't create ambiguity. If I ask you what f of 3 is, we can definitively say 4. In fact, we have 2 points that are pushing us to that conclusion that f of 3 is equal to 4. This would be well defined and would still count as a function. So not necessarily important that the -7 hasn't been used just yet. Repeated values of y are fine. They just can't be used already for that particular value of x when we are considering this. So for instance, something like 3, 2 would disqualify it from being a function. But 3, 4, we're not adding any new information there. We're not changing our relation at all. All right, let's take a look at number 7. We are being asked to evaluate the function for a particular value. In this case, we were told that our function f of x is equal to -12 x squared. And in particular, we are trying to evaluate at x plus h. Evaluate as a verb very simply means taking our x plus h and everywhere we see an x, replacing it with that x plus h. I do not need you guys to simplify beyond this. The only thing I really care about in terms of simplification is those like fractions within fractions. But certainly we could, if you do want to simplify, make sure that you are doing your Punnett square or foiling or however you want to do it, not distributing the squared. We would get like x squared plus 2h, 2hx plus h squared. And then we're multiplying that by -12, which you could distribute, get like -12x squared minus 24xh minus 12h squared. But of course, both of these are perfectly acceptable. Either one is fantastic. All right, let's take a look at number 10. I know I did this one in class today for everyone, but we'll go ahead and do it here as well. Page. So number 10, trying to identify the domain of a particular function. In this case, we are looking at the square root of 9 minus x squared over x squared plus 3x plus 2. Now, when we are trying to consider the domain of a particular function, there are two rules that we need to consider. First, we need to make sure that we are not dividing by 0. And the second is that we need to make sure that we are not taking no square roots of negatives, or like roots in general of negatives. That's kind of at the very least our basic intuition. Certainly that is something that we can kind of flesh out a little bit later. But for now, this is sufficient, and this is what we will see for the most part. So we ask the question, do I have to worry about dividing by 0? And the answer is yes, we do need to worry about dividing by 0, at least potentially, because we have some kind of expression for x in our denominator. Maybe there aren't any values of x that make that become 0. Maybe there are. At the very least, we have to check. And we certainly do need to worry about taking square roots of negatives because we do have an expression that is in a square root here. So at the very, very least, we do need to check. Order here does not matter. You can do this any way you'd like. I'm just going to kind of go one rule at a time and modify my domain as we go. We need both of these rules to be satisfied. So we'll throw out x's for one rule, and then we'll throw out x's for the other rule from the remaining x's that we have. I'm going to start with rule number 2. Not for any particular reason. Again, you could do this in any order, and that would be totally fine. So in this case, for our second rule, we want to make sure that there are no negatives under square roots. The way we can take that and write that as an equation, we need to make sure that the inside of our radical, in this case 9 minus x squared, is not negative meaning greater than or equal to 0. Okay, there are ways to solve this. We did not look at, for this particular unit, solving these kind of rational and polynomial inequalities. We will return to this in unit 2. But for now, solving it as much as we can, whether that's subtracting 9 divided by -1 or adding x squared to both sides, you should get that x squared is less than or equal to 9. Remember, when dividing by -1, that inequality is going to flip. And here is where a lot of people made a pretty big mistake, or do make a pretty big mistake, in trying to take the square root of both sides and getting x is less than or equal to 3, which is a problem for a couple of reasons. The first and foremost is that you are neglecting the possibility of plus or minus. And because of this possibility of plus or minus, this inequality doesn't behave very well. And so what I prefer to do, it's unfortunately a little bit more vibes based, which I think can be fine, but is maybe a little bit harder to kind of impart, is to just kind of think logically through what values of x actually work for this expression x squared is less than or equal to 9. And with a little bit of observation, what we can find is that only particularly small values of x are going to be ones that we want. In fact, the largest value of x that we can see from the positive direction is going to be 3. And the smallest value of x, or maybe the largest negative value of x that we can see, while still maintaining this statement to be true, would be -3. And so according to our second rule here, we need to throw away all positive numbers bigger than 3, all negative numbers smaller than, more negative than -3. Notice here we are including -3 and 3 because we can take the square root of 0, that or equal to being very important there. Okay, and then we can consider what's going on with our first rule, kind of in tandem, which says that we want to have no dividing by 0. All right, how do we translate the sentence, or the statement, the sentiment, into an equation? Well, dividing by 0, we need to make sure that our denominator, in this case x squared plus 3x plus 2, is not equal to 0. In this case, we have a quadratic offset from 0. We have a couple of different ways that we can solve this, but the main one that I'm going to highlight here is by factoring. Two numbers that multiply to make 2, that add to make 3, are going to be x plus 2, or 2 and 1, which gives me x plus 2 times x plus 1, not equal to 0. The logic behind an inequality is a little bit subtle relative to the equality. I'm not going to worry about it too much here. We're going to attend a little bit to precision, but not really the focus here. The two equations that must be true are that x plus 2 needs to not be 0, and rather than the typical or, that x plus 1 needs to not be 0, from which we get that x isn't allowed to be -2, and it isn't allowed to be -1. So in addition to not allowing large values of x, anything larger than 3, anything more negative, larger than -3, we also need to throw away the -2 and the -1. On our domain, starting with our smallest possible value, -3, we will continue right up until we get to -2, at which point we will skip it and then go from -2, continue to -1, skip it, and then go all the way to 3. All right, number 11 here. We are asked to find, given a function, f of x equal to 1 over x minus 2, asked to find the average rate of change on the interval 1 to 1 plus h. Average rate of change is just a kind of pretentious way to say slope. And our formula for slope, y2 minus y1 over x2 minus x1. In terms of the information that we have already been given, you guys are doing a really good job of this in class, but just making sure that this is our x1 and this is our x2, right? I'm giving you the x values, not the y values. How then do we find the corresponding y values for these particular x values? Well, we're going to take these x values in and plug them into our particular function here. So looking for f of 1 and looking for f of 1 plus h, which give me 1 over 1 minus 2, which is -1, and 1 over 1 plus h minus 2, which gives me 1 over h minus 1. All right, we have our x2, our x1, we have our y2, our y1, and so our average rate of change is going to be y2 minus y1 over x2 minus x1. All right, that's pretty solid already. The only cleanup here that I would really say I want to see is I don't love having like fractions inside of my fractions. It's just a little bit messier than what I would like. So a little bit of cleanup here before we try and deal with that. So 1 over h minus 1 plus 1 minus a negative, and then the 1 and the -1 in my denominator are going to cancel. Now, one nice way that I can get rid of fractions from my numerator is I could try multiplying into my numerator by the denominator that I'm trying to get rid of. So in this case, I'm trying to get rid of h minus 1. So we can go ahead and multiply my numerator by h minus 1. To maintain equality, if I'm doing it to my numerator, I have to do it to my denominator as well. And when we do so, we are going to get the 1 over h minus 1 times h minus 1 just becomes a 1. That's why we're doing this. Plus 1 times h minus 1 over h times h minus 1. A little bit of simplification on top gives us h over h times h minus 1, and cancellation 1 over h minus 1. This would also be like, again, in terms of like, I don't care all that much about simplification, that would be perfectly correct. This would be perfectly correct. All of those are great. All right, let's take a look at number 13 here. So we are given a function. This function has something that we will talk about in Unit 2, which is a vertical asymptote at x equals 3. And looks something like this, where these points here, where it does in fact touch, are the points 1, 0, and the points 4, 0. We're asked to do a couple of things. We're trying to find the interval where we are increasing, decreasing. We're asked for local maxes and mins, and then absolute maxes and mins here. For increasing, decreasing, we want to make sure of two things. One, we always want to make sure that we are moving left to right. I think students have a tendency to follow the arrows, and that is going to lead you astray in this case. We don't care about the arrows. We're always starting from the left and moving to the right. And since I am asking you for an interval over which this is happening, we are always looking at the x values for this particular function. So for instance, starting all the way to the left at negative infinity, I am increasing. Notice my y value is getting larger and larger and larger, increasing from negative infinity until I hit the x value of 1. And I am also increasing from starting at 3 and going all the way up till 4, moving left to right, right? These two kind of regions of my graph here. Where's my arrow pointed up? And then I am decreasing everywhere else. You could theoretically also be constant in some places, but here I'm not. Right here, we are going down everywhere else, which will be everything from 1 to 3 and everything from 4 and on. Right. We are also asked for absolute and local maxes and mins. So local maxes and mins, these are going to be those values that are larger than everything that is around them. So local max, I would say we have two of them, which are going to be the points 1, 0 and the points 4, 0. As for local mins, I would say we don't have any. There is no point that we can point to and say definitively this point is definitely smaller than everything else that is around it. My E before was fine. That's fine. That we can definitively say, yeah, everything around this is that everything around this is larger. I can always find a point that is smaller close to that point. And then for our absolute max, same thing. What is the absolute largest that we get? In this case, it's a tie. And so because it's a tie, we'll go ahead and list both. Often you would pick which of these is bigger, but in this case, they're the same size. And then our absolute min, kind of same idea. I go really, really, really negative. I can't point to a specific point that is the lowest value of y, and so there is no absolute mean here. All right, let's take a look at 15. Kind of reaching the end here. So you're told that f of x is equal to 1 over x plus 3, and g of x is equal to x squared minus 4. We are trying to find g of f of 2. So what, in terms of function notation, is this asking me to do? Well, it is very specifically saying everywhere in g that I see an x, I am going to replace it with an f of 2. So instead of x squared, we're going to have f of 2 squared minus 4. What is f of 2? Well, we can figure that out. F of 2, everywhere I see an x, replace it with a 2 in f. 1 over 2 plus 3 is going to be 1 over 5. And so g of f of 2 is going to be 1/5 squared minus 4, which you can leave things like that. That's totally fine. It works out to be negative 3.96 or negative 99 over 25, something like that. Okay, 16, transformations. We are given a function f of x, and we are told that it has been transformed in 2 ways. It has shifted up by 3, and it has reflected about the y-axis, which we should translate as a horizontal reflection. Now, up by 3 is not too bad. Y transformations kind of do exactly what you'd expect. So we go from f of x to f of x plus 3. This is our up by 3. And then from there, reflecting about the y-axis, that's telling us keep your y's the same, but change up your x's. This is going to be f of negative x plus 3. Not too crazy. I see a lot of people say like f of x equals something, or like f equals negative x plus 3 or something. This is what we are talking about, right? The transformation, our new function, is we take f of x and we're doing something to it, and these are the two things that we are doing. Burn this into your brain. This is, I'd say, probably one of the most missed things that I see, even from this study guide in past years, is that people really, really, really struggle with how they present these transformations. And it is exactly as you see there. Okay, number 17. We are asked to find, or really confirm, but find the inverse function. So here, we'll write this a different way. So we're told that f of x is equal to 1 over x, and we are trying to find f inverse of x. All right, so the way we do this, inverse functions, not too crazy. We are going to take our x's and our y's, and we are going to swap them. So instead of y equals 1 over x, we have x equals 1 over y, and we're trying to solve for y. A couple of different ways that we can do that. I'm going to just stick with kind of the most straightforward, which would probably just be multiplying my y over to the other side. In doing so, I get that xy is equal to 1, and dividing both sides by x, that y is equal to 1 over x. So we have a kind of a funny instance here where our inverse function is actually the same as our original function. Kind of a neat thing here. If we needed to confirm this, we could always do so with function composition. So if we take our function and plug in the inverse, we should see cancellation. We should just see, at the end of the day, x. So 1 over x dividing by 1 over x is the same as multiplying by x over 1, which does equal x. which doesn't look canceled, but it is. This is what cancellation looks like for composition. All right. And lastly, a couple of little quick ones on linear functions here. So looking for the two equations for the lines given passing through 2 points. So 1, -1, -2, and -7, 7. And the other, -1, -2, and 5, 2. All right. So I'm just going to do point slope. Frankly, it's the easiest one, and I'm lazy and don't want to do any others. So first slope here, this is going to be 7 minus -2 over, so y2 minus y1 over x2 minus x1, for which I get 9 over -6. We can clean that up a little bit, -3 over 2. And for my second slope, I get 2 minus -2 over 5 minus -1, 4 over 6, which cleans up to be 2 over 3. In this case, they both share a point, so we could use that point, leave everything the same. What you use as x1 and y1 and x2, y2, it doesn't really matter for our equation. Regardless, we will end up with something like y minus -2 is equal to -3 over 2 times x minus -1. And similarly, y minus -2 equals 2 over 3 times x minus -1. And number 20, what we can say is that these two lines are perpendicular because the slopes are opposite reciprocals. A quick way to check, are two slopes opposite reciprocals? If you take their product, you are always going to end up with -1. So they are, in fact, perpendicular lines. All right, hopefully that was helpful. In addition to the study guide, remember that there is that additional, the additional resource in last year's test. If you have any questions as you are either working through the study guide or looking at the questions from last year's test, do please let me know, and I will do my best to get back to you in a timely manner. But beyond that, I hope you guys have a fantastic rest of your night, and I will see you all tomorrow. Take care.